Good day! With this video lesson, we're going to discuss the topic problem solving involving sampling distribution of sample means under your probability and statistics. Our lesson objective: at the end of this lesson, you are expected to solve problems involving sampling distributions of the sample mean. So let's have some review about your central limit theorem and the formula in computing for the variance and standard deviation in dealing with your finite and infinite population. Your central limit theorem states that as sample size become larger, the sampling distribution of the sample means approaches the normal distribution, regardless of that variable's distribution in the population. So, what we need to take note about your central limit theorem is that even your n or your sample size becomes larger and larger and larger, still your sampling distribution of the sample means approaches the normal distribution, regardless of that variable's distribution in the population. So these facts hold especially true for sample size is greater than or equal to 30. So we apply your central limit theorem if your sample size is greater than or equal to 30. The more samples you have, the more it will likely to be a normal distribution. Now, dealing with the variance and standard deviation of sampling distributions, there are formulas uh, for these two. So the formula below can be used to calculate the variance and standard deviation of sampling distribution. So first is for your finite population, the second is for your infinite population. So under your variance, for your finite population, that will be equal to sigma square x is equal to sigma square over your sample size multiplied by population minus sample size all over your population minus 1. Your big letter N here is your population and your small letter here is your sample. Then for your infinite population, so your variance is equal to sigma square x is equal to sigma square over your sample size. For your standard deviation, your sigma x is equal to your sigma, which is your standard deviation for your population, over your square root of n, which is your sample size, multiplied by square root of your population minus your sample size all over your population minus 1. So that will be your for finite population dealing with your standard deviation, and for your infinite population, your sigma x is equal to your standard deviation for your from your population over your all over your square root of your sample size n or your sample. Now dealing with your finite population, there's a corrector factor for your finite population and can be calculated using the square root of n minus n all over your n minus 1, or square root of your population minus your sample all over your population minus 1. So we use this correction factor when we're dealing with your finite population. So this will be your finite population correction factor. For our lesson proper, the central limit theorem is one of the most fundamental concepts in statistics because it explains the use of methods of normal distribution for a variety of problems. So again, we simply apply your central limit theorem if your sample is greater than or equal to 30, no, and the distribution of the sample means approaches your normal distribution. So this theorem justifies that the sampling distribution of the sample means is closely normally distributed. Whenever the sample size is large, and no matter what the shape of the population distribution of the mean is. So regardless of your sample size and the shape of the population distribution of the mean is still your sampling distribution of the sample means is closely normally distributed using the concept of your central limit theorem. Again, regardless of your sample size, regardless of the shape of the population distribution of the mean, then the sampling distribution of the sample means is closely normally distributed. So here is the formula for C score. Then there is formula for your one sample and for your multiple samples. Now, for your one sample, your C is equal to X. Your X here is your raw score minus your population mean mu all over your population standard deviation sigma. So this will be your formula in getting your C score in dealing with your one sample. For your multiple samples, your C is equal to your sample means, which is your X bar, minus your mu, which is your population mean, all over your sigma over your square root of your sample size n. Your sigma here is your population standard deviation, then your n is your sample size. So here is the formula for your C score dealing with multiple samples. Now, the central limit theorem justifies the use of this formula when computing for the probability that x bar or your sample mean or the sample mean will take on what value within the range in the sampling distribution of x bar. So we simply use the C-score formula, no, for us to deal with your central limit theorem and dealing with your one sample and the multiple samples. Then we need to uh, substitute the given values for your raw score, your population mean, your population standard deviation, your sample mean, and your sample size. For example, or problem, so the average weight of women is 165 cm with a standard deviation of 15 cm. Assume the variable is normally distributed. So what is the probability that the height of the woman will less than 150 cm if a height of a woman is selected? For letter B, what is the probability that the mean of the sample will be less than 150 cm if the sample height of 6 women is selected? So for our solution or solutions for letter A, so what is the probability that the height of the woman will be less than 150 cm if the height of a woman is selected? So there is a given value here for your x, which is your raw score, which is 150. Then your mu is your population mean, which is 165, and your population standard deviation, which is 15. Now, we are looking for the probability that the height of the woman will be less than 150 cm. Height of a woman is selected denoted by, so we use this probability notation that your phi or your probability of x is less than 150 because we're looking for the probability that the height of the woman will be less than 150 cm. So we simply apply this for probability notation that your p of x, which is your raw score, is less than 150 because we want to find the probability that the height of the woman will be less than. So there is a keyword here, less than, so we need to convert this words no into symbol. The formula that we can use for this one is your C is equal to raw score minus your mu over your population standard deviation sigma will be used to standardize 150 since we are dealing with a one sample obtained from the population. So we're dealing with the one sample obtained from the populations. That's why we use this. Your C, which is equal to your x minus your mu all over your sigma. Now here, so there is a given value for your x, your mu, and your sigma. So we just simply substitute the given values to your given formula here. So as we substitute the given values for our C score, then your C now is equal to 150 minus 165 all over 15. So as we simplify, your 150 minus 165 is negative 15. Then we copy your denominator, which is 15. So negative 15 divided by 15, a positive 15. So that will be equal to C is equal to negative 1. So if we're going to flat no your negative 1 in your normal curve and we follow that your probability and we're looking for the probability of x is less than 150, so we consider those uh, values of C score less than negative 1. So as you can see, if we plot this negative 1, so this will be your negative 1 here. So in your in your normal curve, there are only 6 C scores allowed. So that's why there are 3 positive C scores here and 3 negative C scores here. So we considered those C score which is less than negative 1. So those area under this portion or the shaded region is the probability that will represent our notation here. Now, so by getting the area under the normal curve, we can calculate. So your P of x less than 150 is equal to your P of C is equal to 1.0. So here, we don't need to write your negative sign because your area from 0 to positive 1 and 0 to negative 1 is still the same. That's why we don't need to put your negative here, no? So your negative represent that your C score is from the left side, and if your C score is a positive value, then meaning to say your C is on the right side of your normal curve. Now applying, so that will be 0.5. So if we get the half of this area of the normal curve, so that will be equal to 0.5. And the area from 0 to negative 1 or 0 to 1 is 0.3413. So we're going to subtract this 0.3413 to the half of the area of the normal curve for us to get the area of the shaded region from negative 1 up to the last part, leftmost part of our normal curve. So your P of x less than 150 now is equal to 0.1587. So this will be the area that will be mapped to your shaded region here. So that will be 0.1587. So therefore, the probability that a random selected woman will have a height less than 165 cm is 0.1587, or if we convert this one to the percent, no, we just simply multiply the 0.1587 by 100, so that will be equal to 15.87%. So our final answer is 0.157 or 15.87. So for letter B, so what is the probability that the mean of the sample will be less than 150 cm if a sample of height of 6 women is selected? So there is a value for your sample mean, which is 150. Then your population mean is 165. Your population standard deviation is 15. Then your sample size is equal to 6 because we consider this 6 women. So we are looking for the probability that the mean of the sample will be less than 150 cm if the sample of the height of 6 women is selected, denoted by. So we simply use this probability notation that your P of your sample mean is less than 150. So there's a key word here, less than, so we convert these words to symbol. That's why your P or your probability notation is P of sample mean less than 150, because we assume that your sample mean is less than 150. And what will be the probability that will be mapped on this one? So the formula for this one, since we are dealing with the multiple samples, then your C now is equal to your sample mean minus your population mean all over your population standard deviation over your square root of your sample size n. So we use this formula because we are dealing with your multiple sample. So here there's a given values. So we just simply substitute the given values to your formula, and our resulting value is 150 minus 165 all over 15 over square root of 6. So as we simplify, our resulting value for your C is negative 2.4495. So draw a normal curve. So here from 0 to positive 3 and 0 to negative 3. So there are 3 negative z-scores and 3 positive z-scores. Meaning to say there are only 6 z-scores allowed in every normal curve. So by getting the area under the normal curve, we can calculate the T of x bar. So it's a typographical, no? So it's x bar less than 150. So is equal to your C less than negative 2.4495. This will be your computed C scores. So what will be the area less than that we can map to the C scores less than negative 2.4495? Because we're looking for less than. So we consider this shaded region as a value of your probability that will be mapped if your X bar is less than 150. Now, first thing to do is to cut your normal curve into two equal parts. So that will be 0.5, 0.5. Same thing with this one. So that will be 0.5. So this will be your 0.5. Then now, if your C is 2.4495, then your area that will be mapped to this C score is 0.4928 using your C table. Now, if we subtract this 0.4928 to your 0.5, this will be your area. So this will be the value that we can map on your shaded region. If your probability, if we're asked for the probability that will be mapped to your sample mean is less than 150, then 0.0072 is the value of that probability. So therefore, the probability that the mean height of 6 randomly selected women will be less than 165 is 0.0072, or simply 0.72%. So if we want to convert this one, we just simply multiply it by 100 and to make it 0.72%. So points funder. So if all possible samples of size n are drawn from a population of size n, which is your population, with your mean u or your population mean and your variance sigma square, then the sampling distribution of the sample means has the following properties. Now, the mean of the sampling distribution of the sample mean is equal to the population mean u. So that's why your mean of your sample mean is equal to your population mean. Now, for number 2, the variance of the sampling distribution of the sample means sigma is given by. So there is a given formula here for your variance for infinite population. And for number 3, there is a given formula for your standard deviation of the sampling distribution of the sample means is given by. So there is a formula for standard deviation once you are dealing with your finite and infinite population, and there is a corrector factor for finite populations, which is square root of n minus n all over your n minus 1. Now, let's deal with describing the sampling distribution of the sample means from an infinite population. So our example problem, so our population has mean of 60 and standard deviation of 5. A random sample of 16 measurement is drawn from this population. Describe the sampling distribution of the sample means by computing its means and standard deviation. So we're asked to compute for the value of your mean and standard deviation. So for the solution, we shall assume that the population is infinite. So there are 3 steps here. So identify the given information. So you need to list down all the given values. Your mu is 60, your sigma is 5, and your n is 16. So find the mean of the sampling distribution. Use the property that your your mean of the sample mean is equal to your population mean. That's why whatever the value of your population mean here will be equal to your mean of the sample mean, which is equal to 60. So therefore, your mean now is equal to 60. So find the standard deviation of the sampling distribution. Use the formula for your infinite, no? So we apply your sigma of your sample mean is equal to your sigma over your square root of n or your sample size. So we just simply substitute the given values for your sigma 5 and n is equal to 16. So our resulting value is 5 over square root of 16. So since 16 is a perfect square, then if we take the square root of the 16, that will be equal to 4. So 5 over 4 is equal to 1.25. So therefore, the value of your mean is 60, and for your standard deviation, so that will be equal to 1 point. So for your activity 1, so the allowance of junior high school students is normal distributed, has a mean of 18.3 pesos and the standard deviation of 1.5 pesos. If 60 samples consisting of 13 junior high school students, no, each are drawn from the population, what is the mean and the standard deviation of the sampling distribution of the means? Assume that the population is infinite. So what will be the value of your mean and standard deviation if you're dealing with the infinite population? So thanks for watching. If you want to like, comment, share, and subscribe, so please do so. Again, I'm Arvin Enriquez, your subject teacher for probability and statistics.